So let's look at the table representation of the previous data was multiplied again. So what we did last time is table multiplied, and then this is what gives us two features, right? This is essentially two dimensions arranged in a tabular format. So we have on one side we have decisions which are documented with a milk is picked or not picked, and then on the second side or the right side we have the corresponding bread which is picked or not picked. So that's the associated study that we did earlier, and the value of the chi-square metric. One limitation of chi-square metric is that it is still dependent. The value, the magnitude of the chi-square metric is dependent on the number of observations. In this case, it is 150, and also based on the number of features that are to be considered against which the decisions were made. In this case, features basically become the categories. And so here there are two categories against which each decision has to be made. And that's why the dependency is there on the total number of observations as well as on the individual row and column, which is essentially the two categories or in a general term feature. And that's why we need to have a countermeasure to rescale this measure so that it is not dependent on the number of observations and number of features as such. And so the first adjustment is called a psi. That's this is and it is basically, it consists of dividing the original chi-square metric by the number of observations, which is n, and this is what we can quickly do by this formula. And we saw earlier how we can extract the chi-square statistic by putting a $sign on the chi.sq variable and getting the statistic value. Please see how that is done. So this is the value 16.10885. This is the chi-square metric we calculated earlier. And what we're doing now is we're calculating the phi metric, which is adjusting for the total number of observations. So what we're doing is we're dividing the calculated chi-square metric by the total number of observations, and then we're taking a square root because that's the second treatment, right? So first, if you go back and look at the chi-square statistic, it is summed over all the rows and columns. So that's the adjustment for the total number of observations. And it is also punishing the difference between observed values and expected values, right? So, and hence we have to make both adjustments one after another. So first we divide by the total number of observations, and then we take a square root. So that's the phi adjustment. So this formula gives us the phi adjustment. Let's take a look at what the value calculated is. And the value calculated is 0.3277. Right? So this is the first metric. And beyond this, there is also a contingency coefficient. So this is another adjustment to ensure that the calculated metric stays between 0 and 1. So this is the contingency coefficient is defined as psi squared divided by psi squared plus 1. And psi is the phi is the metric that we calculated earlier. So it's phi squared divided by phi squared plus 1. Right? That's the contingency coefficient. So let's calculate that quickly. So we are defining a function. This is the custom function that we need to write in R. And the function will take an input parameter and it will return the psi squared divided by psi squared plus 1, right? So essentially, so this function will give us the value for the newly calculated metrics. So what we're going to do is we're just going to pass on the earlier calculated value, and let's print that value, which is 0.09. And since it is that x square is retained from the earlier chi-square test, and that's why we probably have to also rename this so that there is no confusion between the earlier calculated chi-square metric and this newly calculated contingency coefficient. So we calculated chi-square earlier, Then we calculated the psi or phi, and then now we've calculated the continuity coefficient. One last remaining metric is Cramer's V. So this basically also tries to add an adjustment with respect to the number of features, or in this case, number of columns and number of rows respectively. Right. So essentially, we're taking the minimum of them, and this is essentially something to do with how the total value of the metric is distributed, whether it's distributed evenly or unevenly, and that will depend on whether number of rows and number of columns are equal to each other, whether they're completely symmetric or they're asymmetric, right? So depending on, and that's why we have to select the minimum of that. So we're selecting the spread of chi-square metric over the smaller dimension. So this Cramer's V retains the adjustment for the total number of observations, but what it adds is this adjustment for the number of rows and number of columns. So the formula is under root chi-square metric divided by the total number of observations n multiplied by the minimum of the number of rows and number of columns, which are the features, or in this case the categories which are being compared to each other. And so let's quickly calculate that. So essentially we will define another function called CV, and we have to pass three different values. So first is the chi-square metric, second value is the total number of observations, and third one is the tabular representation of the input data set, so that we can calculate the number of rows and number of columns respectively. And that's how we calculate this. So Cramer's SV variable is basically assign a value, which is chi-square metric, which is passed on the input variable, divided by the total number of observations, which are calculated by passing the total number of rows of this metric database or data set, and then we are doing calculating a minimum of the total number of rows and a tabular representation. Then we subtract 1, which is for the degrees of freedom, and similarly we calculate the total number of values in the column structure, and then we subtract 1 from it, and then take a square. So that's how the Cramer's SV is calculated. So let's quickly do that here. So the variable CV contains that, and we create another variable called CSV, and we can name this variable the way we want to. But essentially, we are passing the chi-square statistic metric, and then we are passing the total number of observations and then tabular structure. So this is done here. And then finally, we have to rename, because if we just put it this way, then it will retain the square. So we'll quickly rename this with Cramer's V, so that we know what this metric is all about, what is it called, and this is how the Cramer's V is calculated.